Introductory Chemistry, Chapter 14, Acids and Bases. So what are some typical properties that would differentiate an acid from a base? So acids typically taste sour, which, of course, when we think of sour, we think of citrus fruit, especially lemons and limes and grapefruit. That's due to the citric acid in it. Acids will dissolve some metals, and it will cause blue litmus paper to turn red. Bases, on the other hand, taste bitter, like if you've ever had to have your mouth washed out with soap. They're slippery, right? Soap is slippery, and it will cause red litmus paper to turn blue. So in just general litmus paper, if it turns blue, it's a base. If it turns pink or red, it's an acid. So now we're going to look at a couple different definitions of acids and bases. So the Arrhenius definition says that an acid will be something that increases the concentration of the hydronium ion, which is H3O+. So hydrochloric acid dissociates into H+ and Cl-, and the H+ then attaches itself to the water that's present, because we're in an aqueous solution, to form the hydronium ion. Your base, however, will increase the concentration of the hydroxide ion. So when sodium hydroxide dissociates into water, you get sodium ions and the hydroxide ions. So this works really well when we're talking about things that just are in water, right? Or strong acids and strong bases, like we have examples here. But what about ammonia? Because we know ammonia is basic. So Brønsted-Lowry acids and bases, in a way, take water out of the equation. Although we're showing how things react with water, right? The definitions before were increasing the concentration of these things in water. So an acid is similar. However, we're looking at an acid being a proton donor. And by proton, we're talking about an H+. Why is that called a proton? Well, hydrogen starts out with one electron. If it loses it, all that remains is a proton. So hydrochloric acid will react with water. The hydrochloric acid loses its proton, the water picks it up, and we end up with Cl- and H3O+. As a base, ammonia will be a proton acceptor. So acids are proton donors, bases are proton acceptors. Why would ammonia accept a proton? Because if we remember about drawing Lewis structures, we would see that the nitrogen atom has a lone pair of electrons. Electrons are negative. We've got a positive proton, right? So they're attracted to each other. So now in this equation, ammonia acts as a base, water acts as the acid, and we end up then with the ammonium ion and the hydroxide ion. So we're still seeing that with an acid, we're creating H3O+, and with a base, we're creating hydroxide, but now it's not based on just a simple dissociation. So what are conjugate acid-base pairs? Well, you have an acid on one side. If it loses a proton, then it's called its conjugate base. If you start with a base, it's going to accept the proton, and then you'd have a conjugate acid. So HA and A- are conjugates, and B and HB+ are conjugates. So when you're an acid, you have a conjugate base. When you're a base, you have a conjugate acid. They are always only going to differ by a number of H's. So we can see HA lost one to get to A-. B accepted one to get to HB+. So it's a difference, right? And when we label, it's always acid and base on your reactant side, and then it's conjugate acid and conjugate base on the product side. And when we look at our conjugate acid-base pairs, once again, it can only differ by an H and a charge, right? We either go up by a +1 or we go down by we subtract 1 from our overall charge. So here's a look at some conjugate acid-base pairs in terms of their strength. So the stronger you are as an acid, the weaker you are as your conjugate base. So we're showing here acid-base pairs. Hydrochloric acid at the top there is an extremely strong acid, meaning complete dissociation in water. Its conjugate base Cl- then doesn't have the power to pick that proton back up. If we go down and we look at some weak acids, if we look here at, let's say, acetic acid, It's not so clear cut, right? We have a weak acid, we have a weak conjugate base. In order to compare which one would be stronger, we'd actually have to look at what we call acid dissociation constants. But for all intensive purposes, if you're strong on one side, you're weak on the other. So a strong base yields a weak conjugate acid. A strong acid yields a weak conjugate base. So let's practice with this, writing out some equations and how these things react with water, acting as Brønsted-Lowry acids and bases. So HF, I see H there, so right away I should be able to recognize that's an acid, which makes water the base. So then when hydrofluoric acid lost its proton, it became the fluoride ion, which is why we make it a conjugate base. And then H3O plus is the conjugate acid of water, right? Anytime I see H3O plus, ding, 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 that should tell me I'm an acid. HNO3, once again, I have an H there in the front, tells me nitric acid is an acid, which makes water the base. And then I lose the proton from nitric acid to become nitrate, and water picks up the proton to become hydronium ion. So here we can clearly see I made an error in this slide because this is the conjugate acid and this is the conjugate base. Down here, I see, all of this stuff here, molecular compound. Why? Because all I have are nonmetals. Well, these are all molecular compounds. But when I see this NH2, this is a derivative of ammonia, which tells me that I'm a base. Right, that hydrogen is not showing up in the front. That's your number one indicator to tell you that you're an acid. So C2H5NH2 is the base, which means it's going to accept a proton from water, resulting in a conjugate base of hydroxide ion, and then the conjugate acid of C2H5NH2+. So once again, the relationship is I lose a proton, then I become the conjugate base on the product side. If I've picked up the proton, I've become the conjugate acid on the other side. So we're just differing by a number of H's and our respective charges. So what are some reactions that can happen between acids and bases? Well, an acid and some metals can be dissolved, and we can form hydrogen gas and salt. So this is a redox reaction, which is also a single displacement, and we would call this gas evolution. So hydrochloric acid can dissolve magnesium to form hydrogen gas and magnesium chloride. We saw this in the chemical changes lab. Acids can also react with metal oxides to form water and salt. So we have hydrobromic acid reacting with potassium oxide to form water and potassium chloride. The most common type of reaction between acids and bases would be neutralization. So we have hydrochloric acid will neutralize sodium hydroxide as a base to form salt and water. We've seen this. This is a double displacement reaction. If we break apart everything into its ions, we can then see that the net ionic equation, if we cancel out our spectators, right, and spectator ions are the same on both sides of the arrow, then our neutralization reaction is an H plus an OH minus yields water. So your spectator ions and neutralization reactions are always going to be from the salt that you form. And your net ionic equation is always going to be H plus OH minus is water. So really, when we think about this, because we talked about the hydronium ion, when H pluses are floating around in water, it basically water hydrates it, which is why we call it hydronium. So it's the hydronium ion and the hydroxide ion that create water. When we have a strong acid and a strong base that react together, this is what is going to occur. You will get your water, you will get your salt, and the way that we can perform this reaction is what we call a titration. And when you do a titration, it is taking a solution that you don't know the concentration of, and you take a solution that you do know the concentration of, which is called the standard solution. So you know the molarity of it, right? We've talked about molarity, moles per liter. And so over here, we're showing a picture of a burette. So in the Erlenmeyer flask here, we have acid. We've added an indicator. In the burette, we have our base. And the solution will turn pink once we have just reached over our equivalence point. And that will show us that we have the same number of moles of acid and base that have reacted. So the equivalence point, as I just said, are when the moles of your acid equal the moles of your base. So in the burette, we have our base that's blue here. In the flask, we have an indicator which is going to change colors based on the pH. We can use this equation when we have a one-to-one relationship between our strong acid and our strong base. It looks very much like the dilution equation. So the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And remember, molarity times volume equals moles. So moles of the acid equal moles of the base. The end point of this reaction occurs when the color changes. So you want your end point to be as close to the equivalence point as possible. So by starting out with knowing what our concentration is in our burette, and we use our burette to determine what volume we use, then we know molarity and volume of our base would tell you your moles. We know the volume of the acid that we started with in our flask. That allows us to calculate the molarity. So calculating unknown concentrations. Calculate the concentration of sodium hydroxide of 25.00 milliliters of this solution were required to neutralize 45.00 milliliters of 0.3000 molar hydrochloric acid. So first we need to write a balanced equation showing the neutralization reaction. Then we're going to look at, we have to make sure we're in liters. So we convert our 45 milliliters to liters. And we pay attention to the fact that this is the volume of hydrochloric acid, not of my base. So I'm going to do the stoichiometry, which says volume times molarity, right? Liters cancel out. And then my relationship is 1 mole to 1 mole. So I've calculated now that I have 0.01350 moles of sodium hydroxide, paying attention to significant figures here. I know my volume, and this should actually be in liters because I converted that, 0.02500 liters. So doing the division tells me then that the concentration of my sodium hydroxide was 0.5400 molar. And problem 2 calculates the concentration of sulfuric acid if it takes 35.00 milliliters of a 0.1000 molar potassium hydroxide to titrate 50.00 milliliters of the acid solution. So once again, we're reacting our strong base with our acid. We show that. We switch partners, right? It's a double displacement. So we get 2 moles of water and our potassium sulfate. So we're doing the same sort of process here, but now we're starting with the concentration of our base and the volume of our base. We convert this to liters and we multiply. Then we use our coefficients from our balanced equation to show that our sulfuric acid has double the power of the proton, right? We have 2 H's here, which is why we need 2 KOH's, because it's H plus OH to give me my water. So I do my stoichiometry, I multiply, I divide. I end up with my moles of sulfuric acid, 0.001750 moles. And I take my moles, I divide it by my volume in liters, which I've converted this to liters, not milliliters. And I get a concentration of 0.03500 molar. Man, I've got a lot of errors in my slides. So the relationship between pH and color and acid-base indicators, and we're going to do a titration. We're going to use phenolphthalein. So you want to pick your indicator close enough to the pH of where it's going to change. If your pH is going to change between 2 and 3 based on the acid or the base that you're using, you're not going to use phenolphthalein as your indicator. So acid-base indicators are weak acids and bases themselves, and they just happen to change color based on whether the solution is acidic or basic. You can actually make your own acid-base indicator at home if you boil up cabbage, purple cabbage, and you can test the pH of different solutions. It's a universal indicator. It changes all kinds of colors based on how acidic or basic your solution is. So talking about strength of acids and bases, your strength comes not from your concentration, but from how well you dissociate. So if you completely dissociate, we call you strong. If you sort of dissociate only a little bit, then you're called weak. So your strong acids are very few. You have hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric acids. Strong acids, that's it. There's your list. There's 6 of them. Everything else is weak. Your strong bases have hydroxide in them. Sodium hydroxide, potassium hydroxide, lithium hydroxide, barium hydroxide. So all of your group 1 metal hydroxides, because they are soluble. And then you have a couple of your group 2 metal hydroxides because they are soluble. So if you're a soluble metal hydroxide, you are a strong base. Once again, there's only a very few. So how do we see whether something's strong or weak just looking at an equation? Well, when we have weak acids and weak bases, we have this back and forth arrow, which says we break apart, but then we get back together. We break apart, we get back together. We know people like that. So acetic acid is weak, carbonic acid is weak. We can look at our acid-base pairs here, right? Acetic acid matches up with acetate, right? Acid, conjugate base. Water acts as a base. Here's our conjugate acid. Carbonic acid, the bicarbonate ion is its conjugate base. Water, hydronium ion, here's our conjugate acid. Our weak base examples, ammonia accepts the proton to form ammonium. So ammonia forms the conjugate acid here. Water acts as the acid to form the hydroxide, which is the conjugate base. And we see a similar situation down here, right? This is a derivative of ammonia. So it's the nitrogen that's going to accept the proton, not the carbon. So you don't end up with C5H6, you end up with C5H5NH3 plus, because that's where the proton goes. So we're weak because we only dissociate to a small extent because we're breaking up and we're getting back together. We're breaking up and getting back together. So moving on to just looking at water. What are the acid-base properties of water? Water can act as both acid and a base. We've seen this in reactions. My bad. So we call it amphiprotic because it can both donate a proton and it can accept a proton. It goes both ways. So water is the most commonly used solvent for both acids and bases because it has this property. And the solute and solvent interactions promote solubility and dissociation, once again, because water does this. It's like, hey, what are you going to dump in me? Well, then I can act as the opposite to help you dissolve. That's what water does. It's pretty awesome. Very accepting. So pure water is virtually 100% molecular, right? So it's not going through this process of dissociation to any major extent. It's a very weak electrolyte then because it's not going to dissociate into ions, but when it does, it forms the hydronium ion and the hydroxide ion. So water plus water gives you hydronium and hydroxide. This equation here is called the auto-ionization of water because it automatically ionizes, right? Auto-ionization. But like I say, we can look at this back and forth arrow, which tells us it's weak. It doesn't do it to a great extent. So when you're drinking water, you're not drinking acid or base. It's neutral. So we can write what we call an equilibrium expression for water, and we'll look more at equilibrium in chapter 15. But what we do is we take the products and we multiply them together, and we call this Kw, which means the dissociation constant for water. So that's what K is. That's what K stands for. It's an equilibrium constant because back and forth arrows say we're in equilibrium. So the product of your hydronium and your hydroxide is going to equal a constant, and that constant, Kw, is 1.0 times 10 to the negative 14, And this is at 25 degrees Celsius. So as we change temperatures, we can actually change the extent to which this occurs. So when the hydronium ion and the hydroxide ion are 1.0 times 10 to the negative 7th molar, this is what we get. This is a constant. It is fixed. You don't have to memorize it, of course. I would provide that for you. So pH, it's our measurement scale to tell us how acidic or basic a solution is. And it's really the power of the proton, right? P stands for power, H stands for the proton. So it's effectively how much hydronium ion do you have in solution. It's defined as the pH equals the negative log of the hydronium ion. So anytime you actually have that little P in front of something, it means take the negative log of that. It is simply a button on your calculator that you will push. So the pH of a solution can be calculated if we know the concentration of either hydronium or hydroxide. We can approximate it using a pH indicator or pH paper, and it can be directly measured by using a pH meter. So some observations that we can make to develop the concept of pH. And our pH scale goes from 0 to 14. However, there have been acids that are less than 0, extremely negative. You can have things that are more basic than 14, but our scale is effectively 0 through 14. So if an acid is added, our hydronium concentration would be higher. Our hydroxide concentration would be lower. So we have an acidic solution. Conversely, if a base is added, of course, our hydroxide ion concentration goes up and our hydronium concentration goes down. Why? Because multiplying these together has to be constant. We saw that with Kw, so it's an inverse relationship. When they are equal, then our solution is neutral, right? So we just remind ourselves that the product of your hydronium and your hydroxide always have to equal 1.0 times 10 to the negative 14th. So in looking at the pH scale and some common items that we might know, so hydrochloric acid, extremely strong acid, right? And strong does not mean high concentration. It just means complete dissociation. So a pH of 0. Your stomach acid, extremely acidic, pH of 1, right? That's why if you get sick a lot, it can erode the enamel on your teeth because it's so acidic. Same thing with drinking things that have acids in them, right? Lemon juice, vinegar, apple cider vinegar, right? Cola, beer, tomatoes, all of these things are acidic. Coffee is acidic. Your urine is slightly acidic. Your saliva is slightly acidic as well, although that can vary. Distilled water, of course, is neutral. Your blood is slightly basic, and that's buffered. And then we can see as we get more basic, so seawater is slightly basic. Baking soda, of course, because that's sodium bicarbonate. The Great Salt Lake, which has a lot of salt in it, pH of 10. Ammonia is a pH of 11, which household ammonia, right? Ammonia is found oftentimes in window cleaner. And then your oven cleaner, and I think like your plumber stuff, you like to unclog your drains, that's really, really basic too. So you want to be careful with that. And then sodium hydroxide is a strong base with a pH of 14. So what are the calculations that we can do with pH or to find pH? So if you know the concentration, then you can find the pH. What is the pH of a 3.0 times 10 to the negative 4th molar hydrochloric acid solution? Well, I know that hydrochloric acid is a strong acid, so that means the concentration of the hydrochloric acid is the same as the concentration of the hydronium ion. So I look down here and see that pH is the negative log of H3O+. So I plug in my 3.0 times 10 to the negative 4. Into my calculator, take the negative log, comes out to 3.52. In terms of sig figs, we go 2 places past the decimal point because we have 2 figures here. So what if I want to know the pH of my KOH solution? Well, the concentration, now I'm looking at a base. This is strong, so it completely dissociates. So 7.2 times 10 to the negative 3 molar. I can take the POH, which is effectively the same, except for now I'm taking the negative log of my hydroxide ion. So the negative log of 7.2 times 10 to the negative 3 equals 2.14. Well, here I see an equation that says the pH plus the POH equals 14. Why do I know this? Because if I perform some math on my KW equation and take the negative log of both sides, taking the negative log of this value is 14. If I take the negative log of H3O plus, that's the pH, I add it then to the negative log of the OH minus, which is the POH. That's just the way negative log operations work. So then to find my pH, I can plug it into this equation and see that 14 minus the POH equals the pH. And I did that calculation here to show that the pH of the solution is 11.86. So here my solution is acidic because my pH is less than 7. Here my solution is basic because the pH is greater than 7, right? And when pH equals 7, that's the only time we have a neutral solution. The last bit of this chapter deals with acid-base buffers. And the most important buffer that you have in your body is within your blood. Why? Because you have to maintain homeostasis. You have to regulate your pH and your temperature. And without doing these things, your proteins will disintegrate. They will unfold, and then nothing does what it's supposed to do, and then you're in big time trouble. So a buffer solution is something that includes a weak acid and its conjugate base, or a base and its conjugate acid. So basically it has what we call a common ion that's the same between them. So buffers act to establish an equilibrium between a conjugate acid-base pair. Because if we have a weak acid in solution, it can react with a base to help neutralize it. If we have a weak base in solution, it can react with an acid that's added to help neutralize it. So you have both weak acid and base in solution. Why not the strong kind? Because we know that when strong dissociates, it never goes back, right? They break up for good, see you later. Well, when we have our weak acid-base pairs in solution, they are perfectly comfortable going back and forth, together apart, together apart. So buffers consist of either the weak acid and its salt, or a weak base and its salt, meaning that we've got that common ion. So your buffer capacity comes from the fact of how much weak acid, what is the concentration of your acid-base pair? Is it 1 molar and 1 molar, or 5 molar and 5 molar, right? The higher the concentration of your respective things gives you a better buffer capacity, because once you react it, it's all gone. So like in your body, your most common one is your, it's carbon dioxide, carbonic acid, and bicarbonate. Why? Because we are breathing in oxygen, we are exhaling carbon dioxide, which means we have carbon dioxide floating around our blood. It can react with water. And so it goes through this series of steps in equilibrium. And this is why, for example, if you're hyperventilating, they tell you to breathe into a bag so that you're actually inhaling that carbon dioxide back, and you're helping to reestablish the buffer in your blood so you don't pass out, right? But anyways, so as I said earlier, if you add a strong base, it's going to react with the acid that's present to neutralize it. If you add a strong acid, it'll react with the base that is present in order to neutralize it. So here, when I'm looking at this, I see acetic acid with water. It dissociates and it gives me the acetate ion and hydronium. So if I have acetic acid and, say, sodium acetate in solution, that would be a buffer because I have both the acid and the base present and it's weak. So how can I identify if a mixture is going to form a buffer? All I'm looking for is that I have a conjugate acid-base pair, which means I'm only differing by an H. That's what I'm looking for, period. When we mix things together, we're looking for, say, a liquid and its salt. or an aqueous solution and its conjugate salt, because we don't just have ions floating around. So in number 1, nitric acid and potassium hydroxide, they do not have a common ion, first of all, and they are both strong. So no, when you put these things together, they neutralize and they're done. This is not a buffer. NH4Br and NH3. Well, if I ignore my Br, I see that I have NH4 and NH3 differing by 1 proton. So yes, this forms a buffer. And once again, I've made a mistake here. NH3 is the base and ammonium ion is the acid. Man, I'm not doing good on this, on these slides. All right, HI and NaI. So even though I see that I have my I in common, hydroiodic acid is a strong acid, so no, it will not form a buffer. HCl and LiClO. Yes, I ignore the lithium and I see that I have ClO in common. I'm differing by an H. And once again, I've labeled these incorrectly because ClO minus is the base and HClO is the acid. And then last but not least, I have acetic acid and hydrofluoric acid. They're both acids. They don't have a common ion. So no, this is not going to form a buffer.